Good day. We continue our lecture on design for strength, and today's lecture is lecture 11. We have been considering in the last class the design for variable loads. Now, you remember that we have been talking about the material property when subjected to varying forces of specific magnitude, and for which we took up a typical specimen as shown here, and this is called the fatigue test specimen, and the results for the fatigue test specimen were plotted in this graph, or the this particular graph, where you can see the entire results being represented in the form of low cycle, high cycle, infinite life. And we considered that this particular situation, this line was basically what we called as an endurance limit. That means, any stress which is occurring beyond this, within this zone, if it is applied onto a machine member, then machine will work for theoretically an infinite life. And at the same time, we have also noted one situation that in case we consider this type of fatigue strength and stress cycles for an materials of non-ferrous and its alloys, then I think that we plotted a graph like that. Anyway, it is coming too close, like, but anyway, that what was main interest was that it do not have any specific endurance limit, and for this type of alloys, and this was a representation for a typical steel material, say mild steel or so. Here also this infinite life cycle, where the endurance limit becomes a flat line, is also not exactly true, but however, we consider such line where which gives you the critical zone, means that beyond this line, if we consider the stresses, then the machine member can withstand an infinite life. However, it is not that always we go for infinite life design. Also, we can have a finite life design, where just by modeling these lines, we can find out the corresponding endurance limit corresponding to some cycles of our interest. Well, if we proceed further, then we see that this endurance limit determination is a very lengthy procedure, and for that reason we can do one one plot like that. A plot of results of simple tension test and rotating beam test gives some correlations between these two strengths. Now, if we go further, then we see that a schematic diagram, where on one side the endurance limit and another side it is an ultimate stress. Okay. Now, this particular plot has been made for different materials of steel. Say this is on ground, this is a machined, this is hot rolled as forged, and this type of graphs represents that the experimental results for these materials have been conducted, one for the rotating beam specimen, another for the simple tensile test, and those results which have been plotted for a typical material have been ultimately joined by a line, and we get a plot as shown here. So, here you can see that once in our hand we have such type of plots, then one need not resort to a time consuming rotating beam experiments. What you can do, that if you are having such plots with you, then knowing the results from the ultimate knowing the results of ultimate strength, one can immediately find out that what should be the corresponding endurance limit. Suppose if this is an ultimate strength of the material, then what one can do is that he can immediately find out, say for a ground steel, what is the corresponding endurance limit. So, in this way the plots of endurance limit and ultimate strengths are available in standard design books or the design handbooks, from where one can take the help, and depending upon the ultimate strength of the material and the material concerned, you can find out the endurance limit. So, this is a very quick method by which one can estimate for the endurance limit. Now, once we have seen such situation, then what has been seen, that a relationship between sigma endurance and sigma ultimate, that means the endurance strength of the material and ultimate strength of the material, can be related by the expression as you can see over here. Now, this is a guideline where for the most of the steel materials, one can say that this sigma endurance limit is 50% of the sigma ultimate strength, provided the ultimate strength is below 1400 megapascal, and it takes a value of 700 megapascal whenever you see that the ultimate strength is beyond 1400 megapascals. Similarly, a cast iron, a broad guideline is that it is 35% of the sigma ultimate, and the similar results also also can be obtained for non-ferrous metals and alloys, where we can see that this sigma endurance is something around 30% of the sigma ultimate. Well, sometimes there is a variation over here, it can come something around 25% to 30% also. As a matter of fact, this depends on the materials to materials, and again the handbooks can provide you with some guidance for considering the endurance limit of a material, provided the ultimate strength of that particular material is known to you. So, for a design purpose, one can take a help of this guideline to find out the value of an sigma endurance limit or the endurance limit of the particular material in concern. Next, what we can understand is that this endurance limit of a material is highly dependent on several parameters. Now, these parameters, which are very commonly known as marine classification or marine parameter or marine factors, it is known by so many names, and some of the examples are being shown over here. These are not the exhaustive list what has been shown here. Several other parameters, marine parameters or marine factors, whatever you can call, are also there, which are responsible for modifying the endurance limit of a material. Now, some examples what has been given over here is that this particular modifying factors for endurance limit depends upon the chemical composition of the material, method of manufacture, stress concentration that is coming into picture, although we have talked about the stress concentrations. Now, the surface conditions, the corrosion, the temperature and the size. Now, depending upon each situation, one required to change or modify the endurance limit what has been obtained either from the either from the rotating beam experiment or from the correlations or the graphs what just we have seen the relationship between the endurance limit and the ultimate stress limit. Now, here we see that few selected factors which has been taken here to show that how we change the endurance limit. Now, please note one thing that here we have mentioned the notation sigma E. What is a sigma E? Sigma E is the endurance limit of the material by which the machine member will be made or manufactured. Now, here sigma EM is the endurance limit of the machine component. That means, this is the material, but when you are considering the sigma endurance limit for the machine component, so many factors are to be taken care of along with the endurance limit for the material which we have obtained for the from the tests or the graphs. Here we are considering some of the very important selected factors. Well, the word important may vary, but anyway these are certain major factors what a designer mostly are concerned about, and all other factors we are just putting inside a K miscellaneous account, where one can choose from the list of marine factors what has been given in a standard design data book. Among the few selected factors, we are concerned about KACUR, means the surface factor. One is the size factor, another is a load factor, another is a temperature factor. Among the miscellaneous factor, we can have corrosion factor, we can have chemical composition factor, we can have a reliability factor, so and so forth. We are categorizing all those factors which are listed under marine classification under the name of K miscellaneous. So, if we consider one by one that how we get the factors, then let us look into a schematic diagram showing how the surface factor varies with an ultimate strength of the material. Now, in this case you can see if the machine member which will be utilized in actual practice, if it is highly polished, then the surface factor comes out to be around 1, although it is not noted here. This is just as schematic representations, no values have been given over here. Similarly, if one considers the factors of surface for a material which is ground, this is unmachined, this is hot rolled, this one is as forged, and this one is in tap water situation, and this is in the salt water situation. So, you understand that simply a machine component which is exposed to a normal water will have a surface finish factor of some value, and which becomes quite low when the same machine member is acted upon by a salt water conditions. That means, lower the surface finish factor, so lower will be the endurance limit, so that the machine member can withstand fewer number of cycles compared to the earlier situation when it is acted upon by a same stress level. So, you can understand that how the surface factor is important when we are considering the design of an machine element. So, considering all these data for the materials, and one can see that an empirical relation for the surface factor can be written in the following form. Here the example, here the relationship what has been given were here is considering some of the surface conditions what has been shown in the earlier figure, but not all. Here you can see the K surface is essentially becoming a function of what? The ultimate strength of the material, and that is written in terms of C1 multiplied by sigma ultimate to the power C2. Now, this constant C1 and C2 assumes different values depending upon the condition of the material. One such conditions, if we just read out, you can see C1 is 1.58, C2 is minus 0.085 for the ground, C1 is 4.51 and C2 equals to minus 0.265 for a machined surface, C1 equals to 57.7 and C2 equals to minus 0.718 for a hot rolled material, and C1 equals to 272 and C2 becomes equals to minus 0.995 as forced, and as I mentioned earlier, the surface finish factor equals to unity when the machine element surface is highly polished. So, this shows the effect of surface finish onto the value of the endurance limit, and this shows one important factor, that whenever someone is going to design a machine element for a fatigue condition, then one has to keep a track of all the situations which might change the values of endurance limit, thus affecting the design for number of cycles in actual practice. The next one we can consider is an empirical relation for the size factor. Now, this particular empirical relation is showing that bending and torsion, if a machine member is acted upon by bending and torsion, the K size or the size factor is defined by the equation d divided by 7.62 to the power minus 0.1133, where the d or the diameter of this particular machine member varies from 2.8 to 51 millimeter. Now, for the higher than above size range, what you can see that size factor depends something around 0.6 to 0.75. Now, one interesting feature you can see from this particular empirical relationship is that if you reduce, if you lower the value of the d, then higher the K size, means what is happening? That means the endurance limit will be lowered by a small amount, and more the size, then K size is gradually decreasing. Now, one of the physical situation is that more the size, more the chances of defects in the material is there. So, that is the reason the size factor decreases with the increase in the size of the material, and this is highly reflected from the equation just what I have shown you on the board. Now, the interesting fact is that for the axial load, one has to take the size factor just as 1. Now, you can see that this empirical relationship only talks about the size factors when you are considering a element which is having a circular cross section and it is rotating. But there could be situations in design when you do not have a machine member which are actually circular in cross section or which are non-rotating. In such cases, still a size factor presents. That means, what I like to mean is that whenever we will be having a machine member of non-circular cross section or non-rotating type, we have to think of the size factor in a little different way. Now, fortunately, such situations are present and we can find out means for achieving such size factor for those cases what I just referred to. You can see that for non-rotating circular bar or machine member of non-circular cross section, one has to compute an effective diameter called d effective. Now, what is the idea of computing this effective diameter? This says that 95%, this is called basically a 95% stress volume concept rather. Okay. Here I have written here as a stress area, I will just show you the reason, and this 95% stress area is equated with same area for a rotating beam. Now, what it says? That means, once we consider a situation, suppose a rotating shaft having a length and cross sectional area A. If you are having some other non-rotating or having a different cross section, say for example rectangular, then also we consider same volume L, and in this case of the circular one we are having a diameter d, and for this area we will be trying to find out the d effective diameter. And because the length in both the cases we are considering to be the same, so we concentrate only onto the area. That means, we concentrate on equating the area from the 95% concept of the stress. Now, what is this one? Once again, just to read, 95% stress area equals to same area for a rotating beam. Then we take up an example, a rectangular area of height h and width b. So, if we consider once again, then what we can expect that for a rotating beam, a 95% stress area is basically something like this, where you draw a thin annular zone. This is a thin annular zone for which the diameter is 0.95 D. So, this one is called the 95% stress area, and equivalently if you are taking and BH, then this is somewhere a 95% stress area. This is H and P. So, if we equate, then we will be trying to find out what will be the equivalent diameter for a cross section like this. So, if we go back to our earlier page, then what we can see is that the same concept what I have just explained through a figure is being repeated over here through calculation. So, that narrow strip of area, that 95% stress area is basically 0.05 H into B, and that is equals to pi by 4 D square minus 0.95 D whole square. This is the annular area what was shown in the figure. So, after computation, this diameter we call as an effective diameter, and that effective diameter is coming out to be as 0.808 H B to the power half. In the similar manner, if it is an non-rotating circular shaft, then one can consider that in that case I am just drawing over here non-rotating circular shaft. This, if you two parallel chords if you draw and separated by 0.95 D, okay, then twice of this area is actually a 95% stress area. Similarly, I think I just draw it once again for your clarity, that what I just meaning to say, if you just take out such areas and then this is 0.95 D, then twice of this area is actually the 95% stress area. Similarly, if you are having a rotating I section or any other section for that matter, you can have an equivalent diameter or what I have just told you as an effective diameter, which can be calculated, for which you can have the references from the design data book, and for each and everything I am just not explaining you but I am just giving you some concepts and examples for few situations. However, from the experience of a designer, one can find out this idea of this K size without going through such formulas. Roughly one can also start a design with, depending upon the sizes, what should be the values of K size, means more the size, lesser the value of K size. Okay. And normally it can vary, well, it is very difficult to say. If it is 51 around, then it will be maybe around 0.8. If it is around 2.8, it will be nearly 0.9 or so, or maybe little higher. So, that way one can find out the size factor. Now, once we have seen this particular one, that I suppose that we will be able to find out the size factor for a given machine member. Next comes the load factor. What is this load factor? This load factor, as represented by K load, is also obtained from the study of various experimental data, and that has been plotted, that has been analyzed to give the factors as has been shown over here. Normally, for the axial load, the K load is 0.923 whenever the ultimate strength of the material is below or equals to 1520 megapascal, and it becomes equals to 1 when it is more than 1520 megapascal. K load is 1, that means there is no change of endurance limit whenever we are considering the load of the bending into account. A bending load is taken into account, and it becomes equals to 0.577 when you are having torsion and shear load. Now, this value I think we can remember that we got such values when we are considering the ideas. What was that ideas? That means, whenever we are considering the maximum distortion energy theory in our earlier lectures, then we found that if we know the sigma yield point, then the corresponding tau yield point was coming out to be around 0.577 sigma yield point, and this result is also very close to the distortion energy theory. So, we can have an idea of the load factor, just to sum up, 0.923 or 1, depending upon whether the ultimate strength of the material is 1520 megapascal, I mean lower than 1520 megapascal or higher than 1520 megapascal. In the similar manner, we can see that our temperature factor is also given over here, and here the temperature factor becomes 1 if the temperature is less than 300 degrees centigrade, and it is taken as around 0.5 if the temperature is around is more than 300 degrees Celsius. Now, here you can understand this temperature effect can create you situations like the creep and etc. So, one can take an temperature effect. Now, as I have mentioned earlier that we do have other situations for the chemical compositions, corrosion, I have not mentioned over here, particularly method of manufacture. It has got many other, I mean only not method of manufacture means different situations, okay, how you have done it, and also the heat treatments. All these are very important for modifying the endurance limit. However, we have just discussed some of the very commonly used modifying factors for the endurance limit. Now, you can see a figure which represents a load cycle. This type of load cycle we have seen earlier while discussing about the typical type of load for the designs, and there we told that we will be coming up later on for more detailed discussions on the variable load situations. Here you can see that load onto a machine member has been plotted in a sinusoidal manner for different times, where you can see this axis is a stress axis and this is a time axis. That means how the load onto material is changing. In this case, we consider that from here this situation is that this is the maximum stress, as you can see. This is the minimum stress, and if we consider this as a maximum stress and this is the minimum stress, so somewhere we are having this what we call as a mean stress or average stress, and that mean stress or average stress is defined by the relationship that sigma mean equals to sigma max by sigma mean by 2. And once we can see that other one, that means this one is called as stress amplitude. Now, this stress amplitude is denoted by the equation. If you cannot see, this is actually entire thing is divided by 2. Okay. So, that means it is coming out to be sigma A, the notation I just write it over here, sigma A equals to sigma max minus sigma mean divided by 2. So, one can find out that from a stress cycle it is possible to analyze the entire load situation or the variable load situation onto the machine element by considering one as an average stress or the mean stress, another which is called the fluctuating stress, and this is also called in the terms of stress amplitude. So, the fluctuating stress component will be represented as stress amplitude and the average stress component will be represented as a mean stress noted as sigma m and the stress amplitude as sigma a. This is a situation which is commonly known as a fluctuating stress condition. In the similar manner, one can find that a repeated stress condition. What is a repeated stress condition? See, it is going to a maximum stress level. It is going to a maximum stress level here, okay, but you can see the minimum stress level, that is a sigma mean, comes out to be equals to 0. So, in case of the repeated stress, the equation of definition for the mean stress and the stress amplitude remains the same. So, if we substitute sigma mean equals to 0, sigma mean equals to 0, then what you can see, the mean stress is sigma max by 2, which is the same as the stress amplitude, which is coming out to be sigma max by 2. Another situation what is very commonly used is the completely reversed stress. In this case, you can see the magnitude of the stress, completely reversed is the magnitude of the stress. This we call as sigma max. What I was just trying to tell, the magnitude of the stress is the same, that means this is an sigma max, which is just and simply is a same magnitude in the reverse direction having a negative sign. So, sigma max equals to minus of sigma mean. So, obviously, in this type of cyclic loading, what you are having, that mean stress is coming out to be 0. That means, there is no mean stress, but entire stress is only the stress amplitude and fluctuating stress situation. So, this is one of the quite severe situation where you have all the effects due to the fluctuating stress, and that is what is actually being done whenever you have seen the fatigue stress whenever you have seen the fatigue experimentations with a particular specimen what has been shown earlier. In that case, you are having a complete reversal of the stress. A load is acting onto it, and due to the rotation, the top fiber is getting a magnitude of stress which is exactly opposite in magnitude than the bottom fiber, and this process continues for a number of cycles. Ultimately, a break comes onto the specimen. So, we know that we have 3 cycles. One is, this is one we have just discussed, is a completely reversed stress. The earlier one is a fluctuating stress, and the next one is the repeated stress. Now, all these results, what has been plotted over here, if is being analyzed in some other manner, then some interesting situation is observed. What is that? Let us see from a plot of all the stress results and combined with the material property like endurance limit and sigma ultimate, we get a interesting observation. This is a plot where you can see these are the data point for all situations, and once again I would like to say that this is just a schematic representation without giving any values over here, but the nature of the test results would follow the manner what has been depicted over here. In this case, what one can see that we are having one as a mean stress ratio. What is mean stress ratio? This mean stress ratio is sigma m, that is the mean stress, divided by sigma ultimate. And on this side we are having the stress amplitude ratio, which is defined as sigma A, by sigma endurance. Please note that onto this zone, if we take some point like that 1.0 means this is based on sigma ultimate, this is based on sigma UL. Now, similarly, if we consider somewhere say something like this, then we can have a situation here. This defining factor sigma ultimate, it is defining factor will be sigma ultimate in compression. So, let us give it as UT and this is an UC. So, that is in the negative side and this is onto the tension side. Now, this stress amplitude is always defined as sigma A by sigma E, and the values are plotted over here through which the line has been drawn. What you can see over here is this is the mean line, this is the line, dividing line rather, beyond which you are having the tension zone, and beyond this on to our left hand side we can see the compressive zone. See that this endurance limit, the stress ratio sigma A by sigma E ratio is just a parallel line to this one. What it indicates? That means really when a member is acted upon by a fluctuating load, but in compressive in nature, then it has got a very less effect on the fatigue strength, fatigue design, and all the situations which becomes grave the moment the fatigue situation comes for a specimen under a tensile type of stress. So, one thing what we can say that if the load is coming out to be tensile, the compressive in nature, one can also somehow or other can ignore these fatigue designs. The reasons being most likely is something like that. Whenever there is an compression, some defects and other things in the machine member, gets squeezed by that ones, and so that the fractures and other things do not develop that rapidly. What will occur in case when there is the machine members acted upon by tensile type of loading, which is being seen over in this particular case. So, what has been done is that this through this data point one can consider some sort of mean line. It could be a curved, it could be a straight line, or the way it had been represented over here. And if one can model that you keep your stress in such a way that it is always below such line, then if you consider that if your points lie somewhere over here away from this line and you model a safe line like this, then your design will be always guarded against the fatigue loading. Such situation has been taken care of by several people, and a typical model of a fatigue failure is being represented in this diagram. Here you can see the abscissa is a mean stress line and the ordinate is represented as a stress amplitude, or you can call this also as a fluctuating stress, where sigma, that means it would have been better. Suppose we write this is as sigma mean axis and this is a sigma A axis, means stress amplitude axis. So, any point A over here, suppose we consider this line, I will talk about this line, then it has got a coordinate sigma m, has got coordinate sigma m comma sigma A, that is x and y coordinates. Here we can see that this particular figure has got three different curves. One curve we can see is that sigma, this curve you can see is joining the line, a straight line joining the points sigma e and sigma y. What it means? That the maximum stress amplitude is coming out to be the endurance limit for the material. This is the material property which it can withstand, that the maximum amount of the fluctuating stress or the stress amplitude what this material can withstand is given by the sigma e value or the sigma endurance limit value. And synonymous to that, if it is a mean stress or sigma m value, then the maximum coming out to be as a sigma yield point. So, this is the line. If we draw this line, straight line what has been drawn already over here is called the Soderberg safe stress line. What the Soderberg stress line is actually giving? This is giving is that it guards against the yield point of a material. Means what we can say, if it is sigma endurance limit, then one can say somewhere here, just schematically I am trying to put it, is the sigma, say, yield point. So, if we join this line sigma yield point and sigma yield point, so this is the yield line. So, Soderberg line is actually guarding against the yielding of a material. Now, let us take up the other line, okay, which is this line. Here you can see the point is the sigma ultimate to sigma endurance. This signifies that you are having a line joining as before, is that it is guarding against this sigma ultimate value and the sigma endurance, and in a similar manner it has got a name after Goodman, and this is called Goodman safe line of stress. And the last one is the, as you can see, it is the Gerber line. This is the Gerber line. Only thing, he has taken the line to be a parabolic, and that is the reason it is also called that Gerber parabolic relationship of for the fluctuating load. Now, all this line and this curve represents a model. A model means how a material, if a material stress or the machine member stress is related to sigma A, sigma m, sigma endurance and sigma ultimate or sigma yield point. So, what we understand is something like this, that whenever you are having a equation relating this line, whenever you will be having an equation relating to this line, or whenever you will be having an equation relating to this line, all these equations will represent a design consideration. As for example, that if we consider the Soderberg line, then any point falling below this one is a safe design. If we consider this line, then any point falling below this line is a safe line. Any point similar manner, any point falling over here is coming out to be a safe line or safe design points. So, in this manner one can model these situations or write down the equation for these all these three curves and get an interesting relationship and use in the design for fatigue situation or for the variable load situation. In the next class, we will continue discussing about these equations, its significance and how we utilize in the design. Thank you. Good day. We continue our lecture for design for strength, and this is lecture 12. In the last class, you remember that we have been discussing about the equations related to the shape stress design in case of fatigue loading, and these are the Gerber line, the Goodman line and the Soderberg line, where you remember that the abscissa was the mean stress and the ordinate is represented as the stress amplitude. Now, if we consider this line, then what we can see is that if we look for the line, if we look for a line, that is, we considered this is a sigma mean stress and this is the sigma A, that is the stress amplitude, and let us consider a line which represents the Soderberg line. So, in this case you can understand the coordinate of this particular point should be sigma y by 0, because you know the Soderberg point or the Soderberg line is actually guarding against the yield criteria, and this we understand as 0 comma endurance limit for the machine element. So, if we consider the equation of this line, then you can see very easily that we get an expression something like this: sigma A minus, just an equation of straight line, epsilon equals to what? 0 minus sigma epsilon sigma E sigma yield point minus 0, and this is sigma mean minus 0, and this, if you simplify, comes out to be sigma A minus sigma epsilon E.